Okay, though. Electronegativity and bond polarity. So let's talk about that. Again, a review, so not too detailed. Real quick video on this. So electronegativity and bond polarity. Electronegativity, remember, is how much an atom wants or hogs electrons when it's in a covalent bond. So this is different than electron affinity because electronegativity has to be in a chemical bond. Okay, and this inherently affects the bond polarity. Okay. Okay, so remember that electronegativity's trend is up and to the right on the periodic table. It increases in electronegativity, right? So why do we care? Well, because I told you so, but also because let's take a look at this molecule right here. This is ethane. So we got these two carbons bound to one another. They each have 2.5 for the value of electronegativity. It's the same, and there's no hogging of electrons, okay? CH, we have a 2.5 versus 2.2 for the electronegativity. It's a small difference, and it doesn't matter, really. It doesn't have any effect on the chemical bond, really, okay? But let's say we have a different chemical structure, and we've got a CH3 bound to a carbon that has a chlorine on it. Well, carbon, again, 2.5 for the electronegativity, and chlorine is 3.2. That's a very large difference when it comes to electronegativity, and so what this does is it causes a partial separation of charges, okay? And that's where the dipole moment comes in, and that's where the arrow with the line through it on the end, it's a dipole. That creates, if the chlorine is pulling electron density towards it away from the carbon, it becomes more negative, getting a delta positive, negative, and then the carbon becomes more positive, becoming delta positive. This partial separation of charges is also going to create what's called a polar bond. Okay, and so we get that because of the difference in electronegativity. But in the above structure, ethane, we don't have a difference in electronegativity sufficient enough to do that, and so this is a non-polar bond, or carbon-hydrogen and carbon-carbon, those are non-polar bonds. All right, so when it comes to the electronegativity difference, if it's between 0 and 0.4, that's a nonpolar bond, nonpolar covalent. If it's between 0.4 and 1.8, that's a polar covalent bond. And then if the electronegativity difference is greater than 1.8, then that's just going to be an ionic bond, and it's probably between a metal and a nonmetal. And you would have known it's ionic anyway. So the exception might be carbon and a carbon iodide bond. So that electronegativity, they're actually really close. They might even be the same. Yeah, but that's the exception. Okay, so we're still going to call that a polar bond. So polarity of molecules. Let's take a look at carbon dioxide and water. Okay, so we've got a CO double bond in carbon dioxide on both sides, and since that is a polar bond, they oppose one another, or they go on opposite directions, and so that dipole cancels out. Okay, and that means that this particular, even though it has polar bonds, that molecule is non-polar. Now, water, on the other hand, it has a net dipole going upward, and that is a polar molecule because of the oxygen and hydrogen difference in electronegativity. Okay? It's also important to note that you really need to be able to draw your chemical structures properly. Otherwise, if you don't have your three-dimensional orientation written down properly, then you're not going to get the right answer in terms of whether or not the compound is polar. For example, if it's trigonal planar versus trigonal pyramidal, okay, that would be bad. Let's check out these molecules. Remember, we've got that practice going. I'm going to talk about practice. All right, so CH3Br, CH2Br2, and CF4. Let's do those ones first. You can pause it and then work on them on your own. So this is the structure of CH3Br, CH2Br2, and then I'll draw CF4 for you. You should know how to do this so pretty quickly, actually, by now, and then also eventually if you aren't already there. Very soon if you're not already there. So looking at the structure is it polar or nonpolar? So we have this CBr bond, which is polar, and the dipole is pointed towards the bromine. And since that's the only polar bond in there, it's projected in one direction, and it is polar. This one, these two are polar bonds as well. And since there's two of them pointed in generally the same direction, it's polar. So CF is a very polar bond. However, there are four of them heading in opposite directions. And so it's like tug of rope, but they're all equally as strong. So they don't get anywhere. So it's nonpolar. Now let's take a look at this carbon-carbon double bond, this alkene compound. We have dipole headed towards the chlorines on the left structure, and then headed towards the chlorines on the right structure, but they oppose one another. They're in different directions. So the one on the right, sorry, that arrow is terrible. Right, the structure on the right, the chlorine, the dipole moment, they oppose one another, and so that's actually nonpolar. But the one on the left, they go in the same direction, and so it is polar. All right, let's take a look at Bf3 and Nh3. This is a perfect example of why you should know how to draw your three-dimensional structures. Bf3, drawn as such. This is trigonal planar, okay? And so we should know that. And NH3, even though it's got the similar formula, right? Three things on that nitrogen, it is not trigonal planar. And so it is actually trigonal pyramidal, okay? Because of that lone pair on there. And that lone pair projects those hydrogens down, which allows the dipole moment to head, well, let's do the Bf3 first, sorry. So the dipole moment heads towards the fluorines, right? 4.0 for the electronegativity for fluorine. It's the greatest on the periodic table. It's nonpolar. They all oppose one another. They're heading in the opposite directions. And then the nitrogen-hydrogen bond is polar too. And if that were planar, it would be nonpolar. But since it is trigonal pyramidal, it is polar because it has a general net dipole pointing upward. Okay. So that's why it's important to know how to draw your structure. All right. Thanks. Bye.